I used to have jazz shoes, and I was in color guard for 1 year. I don't know. And I know it was my 4th period. We were talking about the pep rally, and we started step team like 2 years ago, right? Yeah. It was weird. Maybe before y'all's time. Who was on the step team in middle school? No one else was on the step team in middle school? I don't know about That's okay. No one else? Thank you. No one wants to admit it? Okay.
No, we didn't have any clubs at Northwest.
I mean, I'm not going to. I mean, it was like.
I was on those steps.
It was like all the way around. I mean, it's been a while. It's been a while.
Come on, you ready?
Okay. I can teach you so many things. Okay. But today's objective is just reactions. Huh? That's a promise. I can teach you some biology too. Okay, so our first bit of this is pretty much review of reactions that we learned in Unit 1. So I'm gonna holler at you, so make sure you're paying attention to help me out with a couple of these. And then we're going to be reviewing our equation writing homework in like 5 minutes, because mainly it's all nomenclature. We just have to understand how to write that in a reaction now. And then we'll talk about 2 types of reactions today, which is synthesis and decomposition. And I have some demos for us. Okay? So law of conservation of matter or law of conservation of mass means what? Izzy?
Basically all mass products have to be reactant. The reactant have to be in product.
Reactant atoms, I'm going to abbreviate for you. Reactant atoms are rearranged to form what? Products. Great. Reactant atoms are rearranged to form products. So the reactant atoms are the same as the product atoms, meaning we have balanced our reaction because we don't want to break the law. The law of laws is the law of conservation of matter or mass. So we must represent this law as a balanced, anybody want to fill in the blank here? A chemical equation. Because an equation could just be like in math class, that right? We're talking about chemical equations. Okay, so what are some ways that we know reactions occur? Austin, give me one. What do we observe?
You can heat up something.
All right, so you might see a temperature change. Okay. Give me something else, Cole. How can you see? This is what y'all put on your Unit 1 test. A new substance forms. That's true, but how do you tell? There's an observation you made. I'll come right back to you. Jasmine. Precipitate could form, which would be evidence that a new substance formed. Evan?
Color change, specifically an unknown one, like
I'll put
one.
Potentially color change, Cole. You want to call a friend? Phone a friend. Phone a friend. He said his friend Savannah. Oh no, Hallie.
I think he was talking to Savannah.
Oh, okay. So we passed the call on. Savannah?
Gas.
Gas evolution. There we go. Those are our technical terms. So those are good ideas to add. And then in general, we have to write some molecules, or excuse me, some elements from the periodic table as molecules, meaning their diatomic form. Nidhi, tell me which are the diatomic molecules on the periodic table. The 7. What do you mean by the 7? Everybody look at the periodic table. Where does the 7 start? Where does the 7 start over here? Nitrogen. And then so NOF, NOF, ClBrI. So we have diatomic nitrogen, oxygen, fluorine, bromine, and iodine. And thank you. So it's the big 7 and hydrogen. You remember this? Okay. And then so off topic. All right, so when do you crisscross charges? Think first. Vanessa.
Good job.
Vanessa. Shh. Ionics, or who else crisscrosses charges? Acids. Good. Because acids are technically covalent, but they act ionic by crisscrossing charges. Okay, and I think that's a pretty good review. All right, so we're going to look at, I think the rest of this is obvious. We're going to look at balancing reactions. All you need to write down, and this was like what our one was about, law of conservation of matter, the way we now show that is by balancing reactions. Who has experienced balancing reactions? Maybe in 8th grade. Like, raise your hand. I can't read your mind. Okay. Just seeing where we are. Guys, what is this? Yeah. Okay, back to me. Okay, so the idea is that we are going to balance our reaction, which I will always refer to as the BCE, Balanced Chemical Equation. And the reason we do that is because we're not criminals. We're going to not break the law. Which law? Matter or mass, okay. So the atoms simply get rearranged, and so through that rearrangement, we then have new products, and we still need to track the number of atoms. So we're still tracking the number of atoms. So this is where you guys left off yesterday. You with me? This is your equation writing homework? Okay, we're going to balance as we go. So we are here. Pay attention. So when you're looking at the zinc, on the reactant side, what you do is to account for everything is you have to consider the coefficient that's here. Well, it looks like all these have a coefficient of 1 in the front because there's no number written. And you look at the subscripts. Well, what subscripts here is zinc? 1. Okay, so we have 1 zinc here. How many zincs are here? 1 because what's right here? 1. Okay, so zincs are good, right? I try not to write a whole lot down because I can easily get distracted by like writing down the number of atoms I have. I try to just do 1 at a time. So zincs are good. How many coppers do I have in reactants? 1 because there's a subscript of 1. How many coppers do I have in products? 1. So coppers are good. Now, do you guys realize that sulfate is the same on the left and the right? Sulfate is a happy polyatomic family. We didn't break it up. It actually stayed together. So I could do one of two things. I can count entire sulfates. How many sulfates do I have here? 1 because there's a coefficient of 1 out here. How many sulfates do I have here? 1. Okay, so I know that if sulfate's 1 and sulfate's 1, then technically sulfurs are balanced and oxygens are balanced. But I also could count how? Individually, right? How many sulfurs do I have? 1 and here? 1 and oxygens? 4 and 4. Is this balanced?
Yes.
Yes, because the atoms are the same on left and right. So what are the coefficients across the board here? 1, 1, 1, 1.
Yeah, do we have to
You don't have to write ones. No. I'm just making sure that if I ask, some people will say that's a 0. If there's not a 1 listed, they'll say it's a 0. Okay. Okay, so next one, magnesium chloride solid decomposes to form, when heated, triangle, when heated, forms solid magnesium chloride and gaseous oxygen. Give me a thumbs up when you look at your reaction. You're good here. Okay, so you guys have your reactions in front of you. You should be checking like just the basic template first. Okay, so everybody work with balancing for me. Yeah, what's up?
Did you decide a triangle above? Yes.
So you have to if it says heated.
Okay.
Yep. So, and that's what that little chart on the top of it was referencing, like heated, electricity, catalyst, things like that. All right, everybody tell me how many magnesiums I have here.
1.
All right, majority rules, most of you guys said 1. So what's happening is there is a subscript of 1 here. This 2 only distributes to where? To what's in the parentheses, right? So that's chlorine and oxygen. So separately, magnesium 1. Over here we have magnesium 1 magnesium. So magnesiums are good. How about chlorines? How many chlorines are on the reactants? Because this 2 distributes in. So there's 2 chlorines over here. How many chlorines over here? 2 because it's subscript of 2. Okay, so magnesiums are fine. Chlorines are fine. How many oxygens are here? So you multiply, right? So 3 times 2 is equal to 6. So 6 oxygens on the reactant side. How many oxygens are here? 2. Okay, you already have your reaction. Oops, I'm sorry. You already have your reaction template. Do not mess with a single subscript. At this point, what's the only thing I'm adding to balance? Coefficient. So I'm going to put a number right here. I'm going to add a coefficient to balance. What coefficient do I need?
3.
A 3, because this 3 distributes itself to the 2 subscript, and I have how many? 6 oxygens. Okay, I'm going to keep doing a couple more out loud. So follow through. This is a 1 to 1 to 3 ratio. Yeah.
Did we have to do like coefficients and all of that last night?
No, I wanted you guys to predict last night by writing the reactions. I'm going through and balancing with you now, okay? Yeah. Jasmine? Oxygen. So the idea is that if we have a singular oxygen, which falls in that big 7, right? If it falls in the big 7 and it's by itself, it's technically not by itself. It's a diatomic. So we must have 2 listed there to represent its diatomic molecule self. So if I wrote N by itself, that would be wrong. I'd have to write as N2. If I wrote F by itself, I'd have to write as F2. All right, so solid sulfur reacts with oxygen gas. Yet again, we've got some diatomics going on here. Is sulfur a diatomic? No, sulfur is not a diatomic. It's not in the 7. Oxygen, is it diatomic? Yes, because it's in the 7, and there's sulfur trioxide over here. So is there a condition here? Yeah, okay. So how many sulfurs in the reactants, everybody? 1. How many sulfurs in the products? 1. So there's a 1 and a 1. Okay, how many oxygens on the reactants? 2. How many oxygens in the products? 3. So 2 and 3. How do I get 2 and 3 to balance? I can't add any half coefficients, actually. You can in thermochemistry, but not right now. Okay. So what's the common multiple?
6.
Least common multiple is 6. So how do I get 2 to equal 6? Multiply it by 3. How do I get 3 to equal 6? Multiply it by 2. All right, so at this point, the 3 times the 2 gives us 6 oxygens, and then this 2 times this 3 gives us 6 oxygens. But what have I done to sulfur? Okay, so I've unbalanced sulfur by putting a 2 in the front, so now when you go back to do the sulfur, add a 2 in the front. Okay, so what some people maybe learned in like middle school or whatever is you write down all your elements like sulfur and oxygen, you put your numbers on each side. Is that how you guys did it? Yes. Just to track it. You can totally do it that way. It really is not, it's not that big of a waste of time, but sometimes you have to balance things and you can do it in your head like this one right here. All right, go with the next one. Solutions of silver nitrate and sodium bromide react to form aqueous silver or sodium nitrate and a precipitate of silver bromide. What could I have written here instead of solid? PT or what else? Or a what? Downward arrow. Okay, all of those mean precipitate or solid. It just means the solid has hit the bottom of the test tube, so that's how we indicate that. Okay. All right, so looking up here, how many silvers? 1 all the way across. How many nitrogens? 1 here, 1 here. How many oxygens? 3 and 3. How many sodiums? 1 and 1 bromines. 1 and 1 is a balance? Yes. What's the ratio across? 1 to 1 to 1 to 1. Okay. All right. I want you guys to work with the person next to you and balance the last or these next 3. Make sure your reaction's right first. Make sure your reaction is right first.
Okay, I'm done now. But, you know, no, this is going to Is it okay if, like, instead of a triangle, you just heat?
Because that's not how this is different. All right, eyes up here. Eyes up here, and I'll take questions.
Yeah, so for the bottom one, the PB and NO3, do you not, or do you put 2 on the K and M?
This one? You mean this one?
Yeah, and then the PB.
Let me explain that one, okay? So up here, this is similar number, whatever this is. This one and this one are similar because they're both decomposition reactions. They make their elemental form, one of which is a diatomic molecule. So that's actually why the fact that I needed 2 oxygens, I had to put a 2 coefficient up front, which met my oxygen count, but then I also had 4 hydrogens, so I needed double this one over here to get 4 hydrogens. Yeah, so that is the main point. Never, ever, 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 ever add a subscript because you already have perfected your nomenclature. You've gotten your reactant or product correct. The only thing we need to balance is add coefficients. Does that make sense? If that's not going to stick with you, you need to write that down. When balancing, only add coefficients. Because once you have your reaction complete, don't mess it up. It's beautiful. You're so balanced. So on this one down here, the last one, the first thing I saw was I had 2 nitrates. You notice that I said earlier, if the nitrate stays the same from left to right, from reactants to product, just balance the whole nitrate as a whole happy family without breaking into N's and O's. So nitrates stay together here, nitrates stay together here. So if I put a parentheses around this nitrate, what coefficient's behind this nitrate here? A 1. Well, over here there was a 2. So I needed to balance the nitrates by putting a 2 coefficient in the front, because this 2 distributes to potassium and to nitrate. So there's 2 nitrates now, great, but that meant I had 2 potassiums, so I probably had already done this already, but the 2 in the front here distributes to the potassium and to the iodide. How many iodides over here? 2 because of this coefficient, the subscript. Okay, on a scale of 1 to 10, how do you feel about balancing? 10, you're baller, 1, you're still horrible. I need to take my survey. You just hold it close to your chest if you don't want to broadcast it. It's like you guys are just throwing up gang signs. Okay. All right. Well, I got a good synopsis there. Let's do a couple more. Eyes up here. All right. So for these next 3, check your reactions first, and then balance with the person next to you. Because AL is a 3 charge, options are 2. Oh, I haven't balanced it yet. I'm having you guys balance it first. This is solid, so this is solid aluminum by itself. It's not an ion. It's not charged. So it's not charging, it's just a pure metal. So whenever we say like, I'm a little slow. But after the 3rd day, this is how it works.
Yeah, no.
2 and 3.
Why do you have more? Well, I'm guessing, like, because if you put it, you have to put it to your because oxygen doesn't match up. Because oxygen has 2 elements, so let's have a 3 on the right.
Alright, eyes up here. 3, 2, 1, eyes. This is the one that everybody gets tripped up on, because the very first thing you do is go, oh, how many aluminums do I have? How many aluminums do I have? 2, right? So you're like, okay, let me just go and put a 2 over here. Good. All right. So then you look over here and you got 3 oxygens, but you got 2 oxygens here. You can't make 2 equal 3. So what do you go up to? 6, because that's the least common multiple. So I need to make oxygens 6. So what do I put out front here? A 2. So that's 2 times 3 is 6 oxygens. What do I put out front here? 3, because 3 times 2 is 6 oxygens, but what have I done to aluminum over here? Made 2 times 2 is a 4, so then you just multiply that and make it a 4. Okay? So, it's that weird 4, but it's a 4. So if you put a 2 there initially, it does not mean that has to stay a 2. So, anyway, and the last one, looking down the bottom, the presence of a catalyst, guys, thank you. In the presence of a catalyst, which is this is an example of a catalyst, you just put that on top of the arrow. Do not try to balance with that. That's going to totally mess up your balancing act, because you can't have manganese in the reactants and no manganese in the products, because then you'd be breaking the law, right? So you can't have that. So once you have 1 phosphorus, 2 oxygens, and then 1 phosphorus and 5 oxygens, you know the phosphori are balanced. You notice the phosphori are balanced. How do you get 5 and 2 to equal each other?
What, 10, yeah.
You go up to the least common multiple, which is 10, so I need to put a what here?
5.
A 5 in front of this oxygen to make me have 10 oxygens total. And then what in front of this PO5? I'm going to squeeze a 2 in there. It's really close together, but there's a 2 coefficient in front of the PO5. So then I'll have 10 oxygens. How many phosphori do I have? 2. So what do I need over here? A 2. So some of it's back and forth, but you still can get to the end and double check everything at the end. Question?
Is there a maximum number for a coefficient?
No. In some of the like catalysis that happens in our body, 144 carbons plus 36 oxygens. I mean, they can get quite big. Okay. Questions before I move on? Yes. Is that this one?
No.
All right, guys, be quiet. I can't hear my people talking to me. Okay, let me talk about that. So what some people have asked me is, now, this is solid aluminum. Every time we look at the periodic table, what we have been doing in the past, we've been referencing the periodic table to look for the what? Like in terms of nomenclature. We've been looking at aluminum and go, hey, that thing's an Al3 plus charge. That's in its ion form. This is just a solid, so we don't put Al3 plus because that's when it's bonding with something, which is why we have a 3 over here. 3 plus for aluminum, 2 minus for oxygen. Those crisscross to make Al2O3. But when it's in solid form, it's just naturally there, sitting there with no charge. Okay? All right. And then we didn't balance this one. What's the coefficient here? 1. What's this one? 2. Because that's 2 ammoniums and 2 nitrates. And then the 2 nitrates are satisfied. What do I need here? Okay. All right, so I'm going to show you guys synthesis first, and then we'll do decomposition, okay? We're actually almost done. All right, we did that. We know our 5 types. Please do not write these 5 types down there on the paper in front of you. Okay, so I'm going to pause. If you think that this in your foldable, this is a great study aid. If you don't think you can, then what I want in your foldable are the general reaction, which here's the general reaction. Okay, start with that. The definition's up there on the top.
Would that be on that?
So basically, the foldable is the notes, but if you don't think you can fit it all because you write big, wait. Then you guys have separate sheets of paper for this. Your definition's up here. That's your definition. This is definition. General formula is a general reaction. It doesn't give you true elements. It just gives you a sample to like show you how things we put together. These two in the red box, because these are going to be what you're going to be able to predict on your own, eventually without your notes. Eventually. Yeah, you need to have these in there. I put minimum what on the board what I want in your foldable, but these are your, like, the stuff in red is probably more important than anything else. So, one second. So what you have here is a synthesis reaction. This is another name for what type of reaction? You saw this in your reading guide?
Combination.
Combination. So it's basically putting 2 things together into 1. So when you heard synthesis before, like photosynthesis, where you make what? What does photosynthesis make? It does not make energy. It makes what? Glucose, right? But just the byproduct of it is what? Glucose is what photosynthesis is really, really supposed to be making, but it mixes other gas. It makes oxygen as a byproduct, and we happen to need that. So synthesis just means to make something. Now, photosynthesis is complex. It makes 2 things. What we're usually looking for synthesis is to make 1 thing from 2 things. So you can see my illustration down here on the bottom. I'll scroll up shortly. 1 thing plus, so this is a red thing plus a yellow thing, made 1 thing, where it kind of meshed together, you can see this is orange, that's kind of what it's supposed to be relaying. Specifically though, we must know the two styles of synthesis. First one is binary. What's binary kind of always mean? Two. And this is when we're making one metal and one nonmetal come together to make what kind of compound? Ionic, right? So in this case, this is an ionic compound. And when we're making our formula and we're deriving our own formula for this, what do we have to do with their charges? Crisscross charges, right? So we have to make sure we do that or our formula will be wrong. Okay? So CCC, I was thinking about that then. Crisscross charges. Okay. All right, so the idea is that we know S means what again?
Solid.
Solid. A lot of times our metals would be solid or gas. So we don't always have to write the state of matter there, but sometimes it helps us to understand what's going on if we don't have the reaction happening in front of us. So binary, two things together come together to make an ionic compound. Cool. The second style is taking a metal oxide, so I have a general equation for that, MO, because M just stands for what? Metal, right? So metal oxide, there's our metal oxide. It can be any metal. We'll do some examples in a second. When you add that to water, it actually makes a metal. What's OH? Hydroxide. So a metal hydroxide is made. Yet again, hydroxide is a polyatomic, so what do we have to do when we make our formula? Say again? Crisscross charges, right? Okay. So let's do two examples. Ready? Can I scroll down just a little?
Yeah, to the number.
Like, right?
Wait, those are not examples?
These are still, okay. These are still kind of general because do you notice I'm not using a true element here? It's just M for metal and O for, okay, oxygen. But in M for non-metal. I haven't given you a true example yet, but these are things you need to know, okay? So let's do, what's your favorite metal, Cole? Aluminum? Gosh, okay. All right, I'll use aluminum in a second. Jacob, what's your favorite metal?
Gold.
Oh, okay, I'm gonna make up a charge for gold. Okay, so AU is gold, right?
Gold.
All right, so gold. We're gonna react that. Grant, what's your favorite non-metal? Okay. Nitrogen? Oh, hydrogen. Okay, let's do hydrogen. Yeah. Okay. So here's silver. Here's gold. AU plus hydrogen. Is this how I write hydrogen?
Totally.
No. Guys, help me out. How do I write hydrogen? I have to write it as a diatomic gas. Okay. Now we're gonna make it combine together to make an ionic compound, which is a weird one, but we're going with it. So if I told you that gold's common charge is 3+, what would our final product be? AU. So that's AU with a 3+.
Parentheses.
I don't have to put parentheses necessarily, but I can. What's the other ion I'm combining with? A hydrogen ion, which would be what charge to your since it's in the back? Okay, well, it's 1 what? Plus or minus? Minus, because I can't add two pluses together because they don't mingle. Plus and minus come together. In chemistry, anyway. All right, so then as I crisscross these charges, what do I get? AUH3. Okay. Now balance it. Go for Austin.
Put 2 in front of it, gold, and then you put a 3 in front of hydrogen, and then 2 in front of product.
So the 2 times the 3 gives me 6 hydrogens. There's 6 hydrogens, 2 golds, and 2 golds. All right, I'll do another one in a second. All right, so for the lower example, I'm going to go with aluminum. All right, so aluminum oxide. What's the formula for aluminum oxide? Think first before you start spouting out wrong answers. Let's make sure everybody's there yet. Aluminum oxide. And 3, 2, 1, go. Al2O3. Aluminum is a 3+, oxygen is a 2-, crisscross down, you're good. So we're going to add that to water. I'm going to write water as HOH, but you can write as H2O. Actually, I'll write as H2O for you guys this time. I'll do HOH later. Okay, so what metal is here? Aluminum. So we're going to make aluminum hydroxide. So write down on your paper aluminum hydroxide. check with the person next to you. Your periodic table should be in front of you because, you know, we're going to be using that part of it. Check with the person next to you. Okay, and come back to me. Kelsey. Kelsey, what's aluminum hydroxide? Parentheses. What's hydroxide? What's aluminum's charge? Okay, so we took Al3 plus and we combined it with OH, which has a charge of what? -1. Okay, and then we crisscrossed them and we got aluminum hydroxide. Now balance. Might take you a second, but you got it. Guys, you're giving up like about 20 seconds into trying to balance something. Take a second and balance it.
Where do you start?
Yeah?
I have a question.
Yeah.
So I don't want to come
Okay. I'm gonna come back to this in a second.
Okay.
Okay, you got it? I'm gonna come back to it. I have a demo for you. I'm gonna do first.
A demo?
Mhm.
What do you mean by
A demo in the back at the fume hood. Meet me there. I'm going to do a quick demo of synthesis, and then I might actually do the demonstration for decomposition too, and then we'll follow up. So I have here a mixture of zinc powder, ZN, zinc powder, and iodine. How do I write iodine in elemental form? I choose is a diatomic, okay? So what I've done here, and you can kind of see the differences there. But I'm thinking we should still work at least for our one. I'm thinking that I will. But there's a little mixture of zinc powder and iodine. Alright, this isn't a really good ingredient. But I'm going, by itself, it might be anything. Sometimes you have to activate a reaction, so I'm going to activate it yourself.
When you say clean,
Well, we're going to see the evidence of chemical reaction. Like the evidence of chemical reaction. Okay, so, hold on. So this is a great evidence of reaction already occurred. Let me look at another. Okay, so that one's not getting it on. Quick recap of what the you can't do a chemical reaction twice since it's already occurred. So, we have some zinc powder. Okay, so we've got some zinc powder. And there's zinc powder. You guys see it's just kind of powdery. And then it's gray in color, right? It's just skin. And then we've got some iodine, which sublime, you're not sublimations. Yeah. What is it? You can't say yes. Solid turning to gas, so when it turns to separate gas. Smell it subliming. Okay, so we're just gonna mix this together. This is iodine. This is what they tend to clean your wounds with. These are even blood. That stuff they put on your arms is iodine. Okay, so this should work now. Should work now. And they want to okay, so this should work. I'm gonna ask this with a drop box. Can you see this? Back of my head. Maybe you guys can use that way. Go across right here, good.
You're not standing in front of me.
Evidence of chemical reactions. You see? Let me see if I can get it going one time. It's probably already done, but go back to slow. There you go. Hold on, we'll go again.
Do it again.
Alright, it's done. Okay, so for the next demo, I have one of the demos. So what I have here, listen up guys, I'm not talking to the human, I'm really talking to you. So we have powder, guys, I can handle it. You're quiet. So you got potassium chlorate. Have the person next to you find the formula for potassium chlorate. Okay, so we have the formula for potassium chloride, yes. It's not, so it's not okay. Okay. All right, let me try to light this thing up real fast. Okay, so what I'm going to do is I'm going to melt this into molten. So it's not going to be lava because it's made of potassium chloride, not magma. But what I'm going to do is I'm going to melt this potassium chloride until it's liquid. So sometimes it takes like 30 seconds. So as this is going to heat, I'm going to see it turn liquid, and then it's going to start to decompose. You see it turn liquid? No. This is just liquid. So I'll tell you what this decomposes into. All chlorates make a gas. Okay, so chlorate either can make chlorine gas, which is plus, or oxygen gas. What do you guys think it's going to make? Oxygen. Yes, but that's going to be too harmful for your so I'll try to melt this thing all the way, but as this makes oxygen gas, it's also going to make potassium chloride. Notice I say chloride, which is potassium chloride. KCl. That flame is alright, so KClO3, which is potassium chlorate, is going to decompose into potassium chloride, and guys, my flame is dying. Wait, is this gas on? Who's gas? Let me see. Open up one of them and see it's on. Okay, alright, so quick, let me reset this off for a while. I know. Oh, why is it off? Hey, Aaron. Okay, I'm going to light this thing back on. Promise. Alright, so back to my storytelling. It's because of residual time. Residual gas. Okay, what's residual mean? Residue, right? We're good. Getting ready. Okay, so I'm going to go ahead and show you the resulting effect of oxygen on a gummy bear in 5, 4,
3,
2,
Let's go.
Thank you, Mackenzie. All right, so what happened there, as you start to write out decomp, so we got about 20 minutes left in class, I'll do examples at the end, okay? What happened there was we actually did a decomposition reaction of a chloride. What gas did I tell you that chlorides make? Oxygen gas. Chlorine gas would kill us all, right? So this is your, now decomposition is the hardest of them all, so they have 4 styles. So that's why you have 4 reactions that you have here to make it template for it. But we did a decomposition reaction and then I did a combustion reaction, which is why we saw the fiery flames. So there were 2 reactions in one there, but you know, we'll go over that later too. Alright, so we'll do examples at the end after we get down our notes. If you cannot remember, if you cannot squeeze this in your foldable, then you got like notes to do too. Things break, one thing breaks into many. Definition, one thing breaks into many. I'll say thing, but I don't really like the word thing. Scroll down some for you, since you're reading the templates down. Especially since you're chatting. And I'll start in a second, so make sure you get your template down for each of these. So do you see my big triangle up there, what I've said decomposition reactions require? Energy. Why do you think I put a triangle? Well, what do we put on top of the arrow?
A triangle.
Say again? Somebody said it. Yes, heat. I specifically mean heat. So remember on top of the arrow to indicate heat, you put a triangle? Yes, yes?
Yes.
Okay, yield symbol. So most of the time these decomposition reactions don't happen just poof on their own. They require a little help. They require either heat being added or electricity can shock them, and then that will kind of ignite the reaction. So sometimes water can do it too, but just an external force helping the reaction to occur. So every single one of these starts with how many reactants? One. And every single one of these produces two products. So for this style, we start with one, we make two. In the synthesis, we started with two and made one. So essentially, these are what of each other? Basically inverse or opposites of each other. Do you notice there are two up here that are exactly what you just wrote for synthesis, but in reverse? Which ones? One and three. So if you know that one is non-metal, or metal plus non-metal makes an ionic compound, then you know the inverse of that, which is the decomposition of that. And if you know in three that a metal oxide and water makes metal hydroxide, then you know the inverse of that. So really, there's only two extra ones because you already know the first two from synthesis. So like I said, many times we're going to make gases as a product in decomposition reactions. So in this first one, the binary compound makes a non-metal. I told you non-metals generally exist at what state of room temperature? There's some that are solids, but some that are gases, right? So this is probably the gas if we're going to be making a gas in all of these. In terms of something being heated up and then reacting, which of these, metal oxide or water, do you think would be the thing that would turn to vapor to gas? Water could form a vapor, especially under warm conditions. So that's something that would potentially form a gas, but you just might see the steam. Which of these is the gas as a number two? Carbon dioxide is the gas. So here's how I remember it. Carbonates make carbon dioxide. It's the carbon-carbon thing. Okay, so carbonates break down to carbon dioxide. And then as you look here with the carbonate, there's some extra stuff that's not being addressed. And that extra oxygen actually stays latched onto the metal. And then chlorates down here, metal chlorates, make what gas? Make what gas? Oxygen gas. Let me just go this way, okay? Metal chlorates make oxygen gas because if it made fluorine diatomic gas, it would kill us, so we try to avoid that. And then the metal chloride kind of stays stuck together here. So, which of these are ionic? I'm going to point to it and you say yay or nay, okay? Is this ionic?
Yay.
Yes, crisscross charges. Is this ionic? It has a carbonate ion, but this is carbonate, guys. You know carbonate is a polyatomic ion. So if it's an ion, the other thing has to be an ion too. So we have to crisscross charges. Metal oxides, yay or nay?
Yes.
Yes, you must crisscross charges. This one?
No.
No. Carbon dioxide, we know that's not ionic. Down here, metal hydroxide.
Yes.
Yes, ionic, crisscross charges. Metal oxide.
Yes.
Yes, crisscross charges. H2O.
No.
No, it's alkyl. And then metal chlorate.
Yes.
Yes, chlorate is a polyatomic ion, crisscross charges. Metal chloride. Yes, crisscross charges. Oxygen gas. No. Okay, so we will be crisscrossing charges 75% of the time. Okay, so let's do some. Oh, here's some good images. If you wanted to take one and kind of use it for your illustration on the front page, you can maybe tell me the name of this one.
Copper chloride.
Copper 2 chloride, right? Because there's going to have to be 2 plus for copper to relate to the 2 chlorine minus 1 charges. Copper 2 chloride breaks down into its 2 substances, so it's 2 elements, meaning copper solid and chlorine gas. Had the reaction right there already. Never mind. Okay. But those might be some good illustrations to indicate how something breaks down into many pieces. Right, so we're going to do some actual examples here. Yeah, so there's two colored circles. I'll go back shortly. You guys can draw whatever you want there, like as long as it looks consistent. Okay. Make sure everybody gets a piece of paper, please. And let's start with the ones on your paper, and then we'll go from there. So, who needs extra papers? Bill's got some more. You have extras, put them on the desk behind you, okay? Yeah. You guys have extras? Alright, everybody look at the place where it says Lecture Notes, Chapter 11, Predicting Products, Part 1. You see that?
Yes, ma'am.
Okay, we are going to predict these products. Now, do you notice on the top in my handwriting it says, write the entire BCE out. Do not just use what I have provided for you here, because this is just giving you the reactants. It does not give you the products. So everybody work with me. Are you ready? Synthesis examples. I'll do the first one. Hydrogen plus chlorine. Everybody, how do I write hydrogen? H2, okay? You need to write down these examples with me. You cannot squeeze it on your foldable and put it on a piece of paper, okay? So H2 plus how to write chlorine? Cl2, because it's a diatomic. Pause. Look at your synthesis examples. Does this fall under binary or the metal oxide one? Binary, because this one is a non-metal and a non-metal, but still is just two separate elements. Now we're going to combine them together into one product. Now, what product do you think that could be? H and Cl. Now, how do I, just as a review, how do I know the subscriptor ones? Okay, well, H gets, no, it's not, you're not smushing them together. You are always crisscrossing charges every single time you form an ionic product. Now, this is an acid, but like Vanessa said, acids act ionically. So what's H's charge? Look at what group it is. 1, so it gets a +1 charge. What's chlorine's charge?
-1.
Because it's in group 7. So when you crisscross the charges, they're both 1. So you get H1, Cl1. That we're good there. Okay, it's not that you're smushing them together and making H2 and Cl2. It's that you're putting them in a new compound. Balance that. What about the 2? Alright, so Izzy, let me do another example before you start disclaiming this, okay? So this is a synthesis example. How did I know this off the bat? Because I start with 2 compounds and I bring it into 1. You guys are helping me out here, okay? I'll let you guys think for a second. Do the magnesium plus oxygen and the barium oxide plus water one. Do those next 2. At least write down the reactants. You weren't in here for an information.
Yes. Except I'm not.
Right now,
No, like, double check that balance.
You're still getting like the one product.
Oh, no, those are the same.
2 and A plus 2.
So you don't have to try
2 and G. I don't know how I did it, but right off.
How about me a 3?
Oh, yeah. Sorry, I wrote this down. Yeah. All right, Emma, tell me what you did for the second one. Tell me the reactants first and we'll bounce to the end. Okay, reactants? Solid, right? Okay. And how did you know O2? Diatomic 7, right? And I'm putting these extra states of matter, but it's just because we're familiar with that as well. What does that combine to make? And what's the name of MgO? Right, so this is a metal plus oxygen makes metal oxide, which is magnesium oxide, which is Mg with a charge of what? Everybody, magnesium's charge. 2 plus and oxygen with a 2 minus. And when you crisscross that, you see they're both 2, so you do what? Simplify to Mg1O1. And then go ahead and balance that for me, Emma.
You have to put 2 the MgO and then O2 on.
Good. Okay. Let's go, Marissa, for number 3. What are the reactants? So this is this barium oxide? Can you tell me where barium is on the periodic table? It's in group 2, so I'm just going to kind of write this small at the top. So what's barium's charge? Plus 2. What's oxygen's charge? 2 minus. 2 minus. So when I crisscross those, what do I get? But what must I do with that to BAO? Okay, so I wasn't sure if that was what you said initially or not. So there's your BAO, and what are you adding this to? H2O. Okay, Evan, pick up from there. Of our synthesis types, is this the synthesis binary or the metal oxide one?
Metal oxide.
All right, so everybody's looking at the metal oxide. What do all metal oxides plus water form? Metal hydroxide. So Evan, pick up from there. What's our metal hydroxide?
It's barium hydroxide.
Which is Ba.
OH2.
How do I write the OH2?
Parentheses around the OH plus 2.
Good. Okay, so if you don't put the parentheses, you're gonna not be able to balance it, period. Okay? So then as we balance this, how many bariums do I have? 1 and 1. How many oxygens do I have on both sides? 1, 2. And then this 2 distributes in here. So we're good with oxygens. And hydrogen's 2, hydrogen's 2, so we're good to go. 1 to 1 to 1 ratio. Now do the decomposition ones, which are right below that. You need to look at your foldables. You don't have these in your head. You need to see your foldables on your head.
Metal oxides. Would it be oh wait, no, maybe not. Oh,
That's one thing. Yeah, that is. I said
Alright, eyes up here. 3, 2, 1. Some of you guys are making great progress. You're learning how to reference your notes for these examples. But as you go, you must be classifying in your head. Okay, first thing I saw was sodium carbonate. A lot of you guys forgot to chew on sodium carbonate. Double check your Polly's charges. So I look at carbonates on my decompositions. What do all metal carbonates break down into? Carbon dioxide and metal oxide. Well, I have a different metal in every single example. So here's my carbon dioxide I made. It doesn't matter if I put it first or second. And then the metal oxide is sodium oxide. Crisscrossing charges give me Na2O. Yeah. Here, on this little two right here. So this is sodium ion and CO3 charge 2 minus. Carbonate's a 2 minus charge, crisscross that, and that's how you get there, okay? So I'm building a lot of last week's stuff, okay? So the next example, fluorides, that is balanced actually already, right? If you check it out, it's balanced. To the potassium chlorate, all chlorates break down into what gas? Oxygen gas, not chlorine gas. So then you must look back at your notes and it says metal chloride. I still have 2 minutes, hold up. Metal chloride, which the metal in this case is what? The metal in this case is what? Potassium. So we make potassium chloride with the 1 and 1 and oxygen. That's not balanced. Give me something to balance with. I see 3 oxygens and 2 oxygens. I can't have both. 2 in front of potassium chlorate and good. Let's do calcium hydroxide, which is number 5. What's the formula for calcium hydroxide?
CaOH.
Ca had already OH. And 2. Okay, think back to synthesis. Think back to synthesis. What made metal hydroxides? What made them? A metal oxide. It was metal what?
Metal oxide.
Metal oxide plus water, right? So this has to break down into a, water is one of the products, and it has to make a metal oxide. What's the metal oxide? Calcium oxide, which is CaO, 2 and 2 down to 1 and 1. You guys can balance. All right, so here's what I'd like for you to do. I have almost finished these with you. Almost. So there's 2 left there. So this is the little piece that I forgot to press out. You guys can pack up now. Okay, you're going to leave. How about I pass you that other door? There are 10 reaction predictions here on your way out. Okay, pack up and okay, grab one on the way out. It's on the cooler. It's on the cooler. Bye. Oh no, the bell hasn't ring yet. We're good. Don't leave just yet. Even go to